Okay, thank you, Matti. Dear President and ladies and gentlemen. So, yeah, I'm Mika Sillanpää from the physics department, and so I will tell about my research work, and it's something like in physics that difference between how we understand this our everyday world, and then there's this individual atoms and molecules. But what is like in between those two seemingly quite different realms of the reality. So in this classical physics, as we have probably studied at school, so which describes almost everything we see by our bare eyes. For example, even space flight can be understood based on something which was invented several hundred years ago by skillful people. And then if we go a little bit away from this, our everyday experience studying cosmological phenomena, for example, then there is the theory of relativity, the two versions of that, which was already invented more than 100 years ago, more or less. And this is then the atomic world, the world of individual elementary particles, which is the world of quantum physics, quantum mechanics. And this is already has been invented quite some years ago, and there's plenty of people who have contributed to this this theory of quantum physics. And this is related now to my work as well. So in quantum physics, the elementary particles are actually waves, not so much particles in some sense. And what we know about waves is that they can, you have to kind of sum up the waves in a way that how you have to think how these wave maxima and minima are kind of aligned with each other. So for example, if you sum up a red wave and a green wave, you get the black wave, which is somewhat more complicated than these two original ones. And this leads to various things obviously in atomic physics and elementary particles also. In some sense, one can think that all the fact that solid matter has its properties is because of the quantum physics. Well, there's the famous Schrödinger equation describing these elementary particles, and then this Greek letter. Physicists use Greek letters everywhere. It's called the wave function, which describes these waves. And if one continues in this very small size regime, but kicks up the energy a lot with these elementary particles, then you can call that you are thinking of particle physics. And there's the particle physics laboratory in Geneva, where this is studied. And this leads to little bit of corrections to, for example, quantum mechanics. And physics, as we know, it's kind of some tower that you build up. It's starting from the bottom, but the bottom usually kind of is never shown to be totally false. But there's little bit of corrections to this. But well, so now I went through this couple of regimes. Physicists like to classify things, humans always do. But what is then in between these several regimes of description of the world? And now my work is related to what is the borderline between this atomic quantum physics and this our everyday experience. So, and these, as I said, these descriptions of these two things seem to be quite different. We have, on the other hand, these elementary particles and waves, and then these balls and space rockets which just fly. And one can say that all that exists consists of atoms which do obey quantum physics. So for example, then do really macroscopic objects obey these wave laws. For example, even living creatures. This is Aku, the cat. And I should briefly mention about more about the quantum physics is that why actually it is nowadays understood that these, when you look at cats or something, you don't see these quanta or waves or interference each because of the so-called measurement. When you measure this in state of these individual particles or cats, the wave function will collapse. This interference will disappear. This was called Copenhagen interpretation, which means that we have this wave, this black wave, which originally consisted of actually two waves. When you measure it, you just get either one, and then that's it. Then the original wave has died. You get either this wave 0 or this wave 1, with some Greek letters again there showing up. And one even more weird feature of quantum mechanics, it's called entanglement, which was invented by also partially by this famous guy who eventually actually refused to believe it or kind of interpret it. Which means that if we have two of these elementary particles, which are these balls, and then if we put them rotate kind of together, there's something like some ghost in between them. They kind of know about each other, although they might be really far away. But once we look at one of them, shine light, then the other one also stops rotating. And then all this kind of thing, then what I have said, it led this kind of guy to think of so-called Schrödinger's cat paradox. If you have again Aku the cat, and think of its wave function, if you put the cat into a box, close the lid, and then you somehow make it either die or not die. It is just there, and it might have died. But before you open the box, it might be in this kind of superposition wave state. But it's only when you open the lid and shine light, then the cat's wave function will collapse either to this alive or dead cat. But in between, it can be in a superposition state that's predicted by quantum mechanics. But well, also in some sense we can think that in our everyday world, let's put the cat in the box and do this same trick, and we just don't know if it's dead or alive before we look in. But the difference is that this kind of quantum cat can so-called exhibit this interference with itself before we look in. So it can kind of, in quantum physics things, in classical physics as well, things oscillate. But here this cat can kind of move back and forth between being dead and alive. So all these things really sounds kind of counterintuitive, so we haven't seen this in real life, at least I haven't, so what's up? What is the explanation? So as I mentioned, this, when you measure the quantum state of the elementary particle or cat, these quantum things don't show up anymore. And nowadays it is thought quite kind of strongly that when these cats or things interact with the environment, put the cat on the table and let it be there, actually then this environment kind of measures effectively the quantum properties of the cat, which means that it stops these quanta from showing up and superpositions. And somebody has worked out some numbers. Physicists always like numbers. So for example, just the collisions with air molecules will measure the cat in 10 to minus 45 seconds. This kind of smaller time than time can probably even exist. And there's even more fundamental limit is that some elementary particles known as neutrinos from the sun, which you can't block at all, they will measure the cat in 0.1 picoseconds. And this time scale is something which is very short, but that still is kind of accessible in the lab, little bit that direction. But even so, these limits mean that in practice you can't observe these kind of dead alive cats, even though it's basically allowed by quantum physics. But you just measure either or see. But anyway, this macroscopic quantum mechanical phenomena has been observed, not with living creatures, but with something anyway quite microscopic. And here, these guys won the famous prize some years ago. They observed this type of analog states in something which you can really hold in your hands, some really big object. Although what was actually used as a CAD was like single elementary particles, but anyway living in quite big object. And then going towards more my work is that if you think of what is like most everyday physical object which you can think of, it's a slowly bouncing ball, let's say. Forgetting about the cats at the moment. Those are still too far from our lab experiments, but if you think of very small balls or something like that, that might be possible to think of. So if we have the ball bouncing, can it be bouncing in the two places, for example, in the same time, as in principle predicted by quantum physics? And in this language, so the cats again. The cat might be really, you put the cat hanging from the swing, and then it might be kind of here or here swinging at the same time, not cat, but again, some like, let's say, little pendulum, which somebody might be able to do by some nanotechnology. And lo and behold, these kind of things have been in some sense already observed by some years ago, even before us. And they made this is an electron microscope picture of some kind of this little moving object, which you can't see move, but it's anyway it moves. And in that, the physicists always like to draw something to oscillate with in time, and that shows something, which is indeed this, that this Schrödinger cat almost is interfering with itself. Some amplitude, for example, of this motion or something, how it oscillates in time. So that was in some sense first observation of these somewhat macroscopic quantum phenomena. But we have been also working on these things recently, and the scheme we have been using, it's such that if you think of two mirrors on the opposite sides of the room, you can see your image many times in them, and so which means the light is reflecting back and forth between the mirrors. But if we now attach one of the mirrors by spring, some other things will happen, which actually eventually will allow us to study these, actually study the motion of this kind of spring mirror, and in that motion perhaps try to see these superpositions of this mirror being here and there or something related to that. And that's called optomechanics, if you think. Well, in our lab we are not using lasers, but we are using microwave lasers. And these mirrors are actually not real mirrors, but they are something which you can think of as mirrors anyway, which are kind of, we make things on a silicon chip by lithography. And they are superconducting metal cavity resonators anyway, resonating at microwave frequencies. We like to draw that kind of diagrams, how to describe these in for electrical engineers. And it actually looks like we make little drums. It's a drum. This is a drum. It's made on a silicon chip. And well, it's a bit hard to see how it actually is, but it's a little drum made of aluminum thin film grown on these kind of silicon chips. And it's a metallic drum. It's about 50 micrometers across, so you can put these like, depending on your hair diameter, but it's about 10 across your hair. So you can't see it with your naked eye, but it's not that small anyway. And now we are claiming we can kind of see in this motion of these drums these somewhat macroscopic Schrödinger cat effects. And yeah, we make these samples here in micronova mostly. Micronova is the aalto nanofabrication, OTA nano. facility which has very nice equipment, electron microscopes, evaporators, so on. Techniques we use here are quite similar to those used for like these micro fabrication of microprocessors, for example. And then we measure them almost at the temperature of absolute zero. And why so? Why just not on the table? Because these, as I mentioned, the environment tends to destroy these delicate quantum features. That's why we work in the low temperature lab. Cool things down to almost absolute zero. Actually, only 10 milli-degrees above the absolute zero, and it needs quite fancy instrumentation. And this is how our dilution refrigerator looks like from inside. When it's here, it's just sitting on the room temperature, but when it's cold, you can't have a look at the inside. And then our silicon chip Schrödinger cats are here in this box, and then that box is hanging here. And this size is something like 0.5 meter, 1 meter. And that size of this chip is like 5 millimeters. And that's one thing we have done recently, so this is mostly for the physicists in you. And so we made so-called squeezed quantum state of this motion of this drum, little drum. If you have studied quantum physics, you might have heard of Heisenberg uncertainty principle, which means that elementary particles can't have the same time their place and speed existing or well-defined, which means this formula. And same time, if you think of this kind of this motion of a pendulum, or in our case this little drum, there's the same thing holding for this position and speed of this drum, which can be written that way. And if you think of this, how this drum vibrates in time, it's this kind of, we describe everything with sine wave oscillations. There's this kind of noise, which can be this quantum noise. And in this squeezed state, the noise will be zero at certain periodic points of time. There's always this inevitable quantum noise, but you can kind of fool the nature or fool the Schrödinger cat by removing the noise at certain fixed, equally spaced events of time. And there's some data we recently measured which demonstrate actually that this little drum head is doing something, not exactly the Schrödinger cat state, but it's doing something which can't be explained by these classical laws of motion, just totally contradicting what Isaac Newton invented a long time ago. And that's some experimental data. We plot the spectra of this motion of this drum, and this lowest spectra means that the vibrations are really small at certain specific instance of time, which shows that we have kind of even fooled the quantum physics that way. And this thing has very nice interpretation, is that the drums, what drums do, they ring, but they cause sound. They radiate sound to the environment. And then one question would be asked, is there how silent you can make this drum? And there's quantum physics sets the limit for that. In principle, there's always the fundamental noise, but we have made something which is actually more silent than silence, because we fooled this quantum physics, and we measured something showed a couple of data points which are where the noise or sound level is below this sound of silence. So, and this has some technological applications. One can, because what we have done is a way to fool. Also, you can think fool noise. You can think these also in simple technology applications or technology terms. One can fool noise, also usual regular noise which you hear, for example, in all analog radios. And if we try to transmit cell phone signal, for example, which always should be thought of as sine waves. So like sine, some wave. Amplitude oscillates in time. And if there's only a little bit noise, you will see this sine wave oscillation, which allows you to talk on the cell phone. This sine wave will transmit the information in a digital communication. But if there's more and more noise, the sine wave will get a bit blocked by the noise from all the surroundings. If your base station of the cell phone is really far away, then the signal gets weak and there's noise. But if the noise is too far, you just can't see the signal anymore. And our work can also lead to real serious applications in this low noise detection and amplification. We use these kind of drum heads, which we shine the microwave laser light onto these vibrating strings or drum heads, and then those get amplified. And then if we do this suitable like noise squeezing or fooling on this noise, then that reflected light can be amplified basically without any noise, and this might have some technology applications. And that's how these silicon chips look like. So it's like this scale is 0.5 millimeter, and then this meandering thing is the superconducting metallic, this microwave resonator. So in the future then, what are the next challenges? So we have done demonstration of these, some kind of Schrödinger cat effects in these properties of sound, or in some also sound is motion. So one can think of really more macroscopic objects, something especially is related to gravitational antennas, where people have been trying to see these quantum noise things for a long time, improve the sensitivity of those using these squeezed properties of motion. Study this macroscopic quantum entanglement, which Einstein didn't like, of moving macroscopic bodies. Even so there's some thoughts we have not been really considering this, that in principle one can think of creating, putting these real, some sense living organisms in these superposition quantum states. Living here means maybe even small viruses. Somebody has calculated it could be possible. We are not trying that. But one thing we might be trying here is to search for some really fundamental new physics, is that if we have these particle accelerators in, for example, in this CERN in Geneva, and they are studying this extremely high energy physics, but if you want to study some totally fundamental new physics, which might be beyond this current understanding of particle physics, then you might need particle accelerators of the size of the solar system. But could be that in this our cavity optomechanical systems you could do something similar, surprisingly. It's not quite on the table, but it's inside this 3 times 3 meter dilution refrigerator. Believe or not, might be possible to do something related to quantum gravity even in these kind of experiments, which is something quite exotic. So I'm going to summarize. So what we heard is what is in between our everyday experience and then the elementary particles and atoms. Those are described by something totally different things in physics. And what kind of physical objects one then looks at it is indeed something like in the micron scale. And those has been shown previously already in some sense to show some things, some properties predicted by quantum physics, these somewhat macroscopic objects. But so we are going to continue this work to observe or try to hunt some new physics, especially observe this quantum entanglement in these moving systems, for example, moving drum heads or other types of mechanical oscillators, and eventually trying to make these tests on animals So this is